Well, welcome everyone to the first informal Astro seminar of the semester. Great to see you all back here again after the big summer recess. And today it will be our pleasure to hear from Vera Gluscevic, who will be telling us about dark matter, neutrinos, and cosmic concordance across scales. And she, of course, it's a very successful career so far, many laurels from best in her class in undergrad to going on to Caltech to work with Mark Minkowski, who's of course well known around here. Then she was a member for 5 years at the IAS, so it's great to welcome her back. After which she went to USC, where she has also had a great group, won many laurels, including the Robbenheimer Outstanding Junior Faculty Award, and I think you recently got tenure. Welcome back to the Institute. I think you'll be here for a year, roughly, so we'll have plenty of time to chat.
Thanks, Alex. And thanks for mentioning my undergrad award. I haven't had that happen in a while. So there's giving talks and then there's giving talks at IAS. So this is like a big recheck for me. I'm still doing okay as an astrophysicist. But in any case, it's wonderful to be back. And I hope I hit the right amount of material and technicality in this seminar. I'm a little disappointed that it's not upstairs in the library because I really like that intimate atmosphere, but I'll make do. All right, so please, of course, as usual, I'm sure you don't need this permission, but do stop me and ask questions and I'll see how far I can get. So it's a bit of a salad of words out there in my title, and that's mostly because I kind of wanted to pack all the things that I find exciting these days into one talk. And I'll try to pull a thread to it that connects all of these different pieces of work. And the thread there is going to be more or less that we've been looking towards many observables in search for new physics. And I'm going to focus on dark matter neutrinos for this talk. But I will also focus on this particular observable, that is the distribution of matter in the universe, as captured, loosely speaking, by this linear matter power spectrum. So this is your primordial situation there, and different colored lines represent different deviations from lambda CDM, where the standard cold dark matter paradigm would be this black line. And if you remove the halos all the way down, that would occur in the WIMP cosmologies, you end up with this no suppression all the way to the smallest possible scales. But again, these different deviations come from different things you can do to the universe at different points in cosmic history. And what I want you to notice is that data so far in cosmology, up until recently really, is piling up on these large scales. We're pushing down lower with galaxy surveys, but really on these smallest scales is where you can hide new physics very efficiently. I want to show you, so this is a summary plot from the SNOMAS white paper, but I'm going to show you my version of this that I really like and I'm going to rely on for this talk. So here I'm showing the transfer function squared, which is just the matter power spectrum in this beyond CDM cosmology divided by the lambda CDM. And so what I'm showing you here is a bunch of lines I'll parse out through this talk. I'll actually use this as a visual for different parts of my talk. I'll talk about different models that are shown here. But for right now, what I want you to notice is that I also try to kind of, with these shaded regions, indicate where the sensitivity of different probes is to the matter distribution in our universe. On the far left, you have the CMB. In between, you have galaxy clustering, weak cleansing. Then you have the Lyman-alpha forest, which I will spend a little bit of time on. And at the very end there, you have substructure, maybe substructure in the Milky Way, maybe substructure that you can reconstruct from strong lensing, and so on. Okay, so here is the parts of my talk. First, I want to touch on a model that we've explored extensively in context of direct detection for dark matter. And this is interacting dark matter that exchanges momentum and heat sometime in cosmic history with baryons, with protons, or whatever else we call baryons in cosmology. And typically in those cosmologies, you get a cutoff that very much looks like warm dark matter. You can shift it around with 3 parameters of the model. Then I'm going to talk about, in terms of structure formation, a very different model where you allow only a portion of dark matter to do something new and non-cold. So I'm going to call that mixed dark matter. And historically, this was referring to a mixture of warm and cold dark matter. In this case, I'm gonna actually mix in some interacting dark matter with cold dark matter. Next one, I wanna cover, again, if I have time, I'll see how far I get to my list here. I want to talk a little bit about self-interacting neutrinos, which to me as a cosmologist thinking about structure formation are really interesting because they give me that excess power. So they're kind of tricky to model in terms of what they do, especially on small scales. So they're really phenomenologically rich when it comes to cosmological signatures. And then at the end, if I have time, I will talk about sterile neutrino dark matter, which I've shifted over to smaller scales, but in reality, then you have three parameters. And the cutoff that you get is very much shaped like warm dark matter, but it's a completely different physics than the free streaming warm dark matter. All right, so those are the four parts of my talk. If I have time, I'll go through all of them, and then I'll tie them all again at the very end. So here we go with the interacting dark matter. I'm going to go back to the work I did some years ago now in collaboration with a whole bunch of people, but most prominently Ethan Nadler, who's now faculty at San Diego, was a postdoc in my group for a while, and other collaborators that I'm going to highlight as I go through my slides. Okay, so in this scenario, what I'm going to do is I'm going to put dark matter in contact with baryons. I'm going to allow these two fluids to interact with each other. And for purposes of cosmology, what we care about is the momentum transfer cross-section. So that is a quantity that tells you the rate of scattering as a function of redshift. Okay, so this equation, I will say this, every equation that I show is there for people who think about these things very quantitatively. If this is daunting and you're not normally parsing out Boltzmann equations, don't worry about it. And the bottom line is that the rate at which scattering happens is proportional to the strength of interaction. So there's my free parameter of this model. And then I also have the mass of dark matter particles featuring in this equation as well. This interaction rate can be dependent on the velocities, relative velocities of particles, which are sourced for most of cosmic history by thermal velocities. So that's why I have temperatures featuring in there as well. But the bottom line is, let's imagine parameterizing this momentum transfer rate by some unknown number normalization times relative velocity to some nth power. Okay? So what happens in cosmologies that feature these kinds of interactions, if you were to plot this transfer function yet again, on large scale, structure is intact. But as you go to smaller scales, you get this beautiful warm dark matter-like cutoff in power. It scales that correspond in some way that I'll talk about to the interaction strength. Okay? So the bottom line from this is that when you look at small enough scales, you should see no structure primordial in the universe. Yes.
Microphysically, what sets the value of n? Is it just like the interaction that you write that on the Lagrangian?
Yes. What operator you're dealing with? Yes. So the power of n depends on the momentum dependence in your operator, typically in your effective operator. And the beauty of this parametrization, by the way, is that it's sufficient to capture effective field theory operators up to second order momentum transfer. You just get a power law, which is really nice. What? Yes.
Do any of these higher order interactions, now you have sort of nonlinearities between the dark matter and the baryon fluid and things like that? Do you do things more than just change the linear power spectrum? Can you do some Gaussian energies just
You can, and I think Yassine Ali Haimoud has been thinking about this. I have not worked on Gaussian energies for these interactions. Yeah, but that's a fair question. Okay, so I want to dig a little bit into the math around this because I want to kind of just build intuition as to what happens in cosmologies like this and how you can use what we know about this primordial matter power spectrum to actually put bounds on these models, but not just with observables that are linear observables that we know how to compute fully, like the CMB, which is beautiful and we can definitely do it. But we can also do more from understanding the substructure in the Milky Way, where we can probe really, really small scales. So so the idea here is that this cutoff happens because of the collisional damping in the early universe, okay? So the scale at which you start to suppress structure, or you stop to suppress structure as you go to larger scales corresponds to the last scale that made it into the horizon before the decoupling of this interaction happened in the early years. So in other words, what I'm saying is, as I lower the value of that sigma naught amplitude parameter, I'm pushing this cutoff towards smaller and smaller scales. So you can imagine there's a limit to which you can use something like the CMB in order to put bounds on these models.
The shape in this plot is for a particular end.
The shape in this plot is for velocity independent interaction, yes, and I'm heading in that direction to talk about the other ones as well. Okay, so I'm gonna fast forward and let me see, am I gonna fast forward? Yes, I'm gonna fast forward and I'm gonna show you the bounds we were able to derive from the Milky Way satellite population as observed by surveys that we have today, like SDSS, DES, and Pan-STARRS, that give us something under 100 satellites down to masses of the order of 10 to the 8 solar mass in terms of halo mass. Okay, so where we arrive here, I just want to put things in context, and then I'll try to argue analytically where this bound comes. Okay, so bear with me for a second. So what I'm showing you on this plot is your classical exclusion plot for direct detection that you must have seen a million times over, except I've shifted my attention towards much larger values of the interaction cross-section and much smaller masses than what we normally look at with nuclear reflow measurements, direct detection experiments, okay? So what I want you to notice is this right here is not the shape that most of us are used to seeing when you talk about exclusion plots from direct detection, and that's because that's the very tip of that excluded region. What you're used to looking at is down here, that little curve that you see that dips right around the scale of the whatever nuclear target mass is. But those exclusion curves have a ceiling to that because these experiments are very shielded, and dark matter that interacts too strongly would never make it into the detectors. Okay, so they only probe so high in the interaction cross-section. And also because of the kinematic limits, again, most nuclei targets are pretty heavy, so you can't impart enough momentum if your dark matter is too light, and that's why this cutoff happens at these scales. So of course, there's many efforts in direct detection community to push this down to lower masses, but the beauty of cosmology also is that it probes really complementary parts of the parameter space, which we do not necessarily access with laboratory in the same way. Okay, so everything shaded here is excluded by the dwarf satellite analysis. This is beautiful work done in collaboration with Nadler and then with DS collaboration as well. And I just want to get your eye to, this is where we were a few years prior with the CMB bounds. These were the leading bounds on sub-GeV mass scale dark matter scattering with protons in a wind-like manner. So again, you gained orders of magnitude there. Okay, so now I want to kind of show you if you're, a theorist like all of us are, and if you're meddling in data, you kind of demand to understand why right here, and what's the shape of the curve, where does all this come from, right? So I just want to throw in there the entirety of the information from the data that's basically sufficient to derive this bound is a limit on the minimum halo mass. In other words, it's the mass of the smallest halos we know exist in our universe. And that's about this number, a few times 10 to the 8 solar mass in our own Milky Way. Okay? So in linear theory, what you can do is you can convert that mass scale to a particular critical length scale and make a claim that, so for this number, I would live right around 30 here, right? So I'm at the scale of a few times 10 to the 8. So the reason I can put these two lines on this plot here is because I'm making a statement that I can do this rough mapping between the mass scale of halos and the length scale in the universe. So this is essentially what I'm, the statement that I'm making. The mean density of the universe times lambda critical cubed, which is related to K critical. So again, linear theory, not very useful. I'm talking about dwarfs here, but let's see how far it gets us, right? Okay, so the story that I told you so far is that I'm making an argument that I can estimate So obviously, I've gotten these curves by running Boltzmann codes in which I've put these interactions, right? This is linear matter power spectrum, I can do that. But I also want to understand it from the physics perspective. I want to get the estimate of where that cutoff is from the parameters of my model. Can I do that? So it turns out for the velocity independent scattering, that's a pretty easy thing to do. And what you want to do is you want to relate the momentum transfer rate, which I'm kind of like in a very, very squiggly way that I represent as number density of your dark matter particles, cross-section velocity or standard quantity, right? So I'm going to relate momentum transfer rate to the Hubble rate. Okay. And what I'm going to say is that when the interactions drop below the Hubble rate, okay, that's when I decouple, roughly speaking. This is wrong in all sorts of ways in detail, okay? But again, I'm doing order of magnitude estimate here. So I'm going to say when that happens, no more interactions. So I can figure out if I can compute this from the parameters of the model. This is where the mass of dark matter enters, right? And the second free parameter is the amplitude of the cross section. So once I specify those two, I know when this thing is going to drop below the Hubble rate. That's a critical redshift. And then I can compute the size of the horizon at that redshift, right? And say that's equal to 2 pi over k crit, which is that quantity over here. Okay? So in other words, if I do this little thing here, again, which is wrong in all sorts of ways, at the end of the day, what do I get? I get k critical, I get where this thing goes down as a function of the parameters of my model. Okay? Again, wrong in all sorts of ways, but let's see what we get. So at the end of the day, I get this critical mass, the smallest mass that halos should have in my universe, as a function of the parameters of my model, this grossly approximated manner. Okay? Now, what that means is once I get that relationship, if I can put a lower bound on this quantity from saying, well, I do see halos that are 10 to the 8 solar mass. In fact, I can measure velocity dispersions and make sure that these things exist in our universe, right? And I am putting an upper bound on the interaction cross-section for a fixed mass. Yes.
But should we compare to the horizon scale or the gene scale?
So the horizon scale gets you pretty good estimate of the bound. Again, we can do this probabilistically by knowing structure formation from simulations of warm dark matter, where we match the cutoff scale with the warm dark matter mass. Okay, so there are simulations that will give us the population of satellites in these cosmologies. All I need to do is make sure to match warm and interacting dark matter, and I'm done. And I can do the full probabilistic analysis and get the bound. This is kind of a sanity cross-check. Do I roughly understand what is going on? Okay, so bottom line is the bounds that I'm showing you here. The first one was before we added DES data. With DES, we gained a factor of a few there. You get within a factor of 2 of this bound. Okay, so full probabilistic analysis and this analytic estimate work kind of pretty well. You're not too wrong. Yeah.
So these observations on the critical halo mass, how uncertain are the numbers? Because I guess you can have pretty good dynamical estimates of the dynamical mass in the inner regions of the dwarf galaxies, but how about the rest of the halo?
Yeah.
How uncertain is that?
Yeah. So this is a totally fair question. There are full likelihood analysis that will tell you the uncertainty of the minimum halo mass, right? So in detail, this is not what we use. So this curve is not derived from a single number. It's derived from matching the cutoff in warm dark matter cosmologies for simulations that we have done. So these are simulations from Wexler and Adler group done back in the day. And then understanding what the full population of satellites is and what their galaxies look like. So this is not an analysis of a single object, it's actually using the whole population to infer these parameters. So there's a lot of marginalization that happened over here over galaxy halo connection and all other things that go into this model. So you're very right that there are uncertainties in the halo masses, but all of that is kind of organically folded into the whole method.
If you fix the galaxy halo connection and don't marginalize over it, how much further down would you go?
We have not done that. I would imagine a lot because you're dominated by the error budget at the same time, right? So in detail, if you guys are familiar with this, the galaxy halo connection is used because the simulations where we have the statistical coverage of various warm dark matter masses and things like that, that are possible to run fast enough for dark matter only, they do not contain baryons. So then we have to be very clever as to how we're populating these halos with actual galaxies. The way we do that is using this galaxy halo connection, but we do allow for the scatter, right, at the phase 10 and quite a bit of it because we do not understand the phase 10 observationally well enough, right? But we marginalize over that. So your intuition is very right that this is one of the dominant contributions to the error budget.
So the answer is
But I don't know
that
the exact quantity.
the answer to the previous question is that you don't actually measure the dynamical masses for these individual sources.
You do
They
not.
come out of the halo occupation distribution modeling,
right.
essentially from the number counts of the faint galaxies that you see.
Yeah, not just the number counts, but their luminosities, their
Luminosities.
radial distributions, and so forth. Okay, and there's a lot of details that are folded into this, a lot of carefulness with making sure that you're modeling a Milky Way-like galaxy that has had an LMC-like companion falling in recently in the accretion history, because that thing corrects your dwarf population by a factor of like 10, 20%, something like that.
Are the strong lensing constraints competitive at all? Do they do anything on those clump mass scales?
Yes, they definitely do. And I think the claim in the field, and this is, I'm not a strong lensing person, I think it's a fascinating field. The claim is that they already can go, a factor of 10 below this mass scale. But the problem, as you can imagine, is that these are massive analysis with like, I don't know, tens of free parameters. They claim consistency with CDM, which is a conversation we should have maybe afterwards, but I think that's a detection of substructure on 10 to the 7 mass scale. But nobody understands where these halos are along the line of sight, like where the host.
Yeah.
It's very hard to convince oneself that this is like a robust bound. But I do think that the sheer potential of this method is really interesting enough for people to push this frontier forward. Claims are very big, and I think everybody feels the pressure to claim the best possible bound. Okay. So let me go to Gabby's question about what model did I choose. So I chose n equals 0 in my previous analysis, but I just also want to show you when I free up n, so when I toggle between different operators for this interaction, what do I get? So here's again my transfer function, and these spaghetti here with dark acoustic oscillations is what you get when you have higher power of velocity dependence. So you get dark acoustic oscillations, and these are a bit of a nightmare. They're kind of like ethos models, but not directly kind of possible to map to ethos cosmology, if you guys are familiar with that. But the idea is the same. You get these choppy excess power on smaller and smaller scales. And that's not something we have actually forward modeled in simulations. So while I can do projector-like approach and tell you what the population of satellites looks like, I would be very nervous doing that because I have no idea what window functions to, how to do this calculation correctly. And unless I have simulations, I have no way to verify that my model actually does a good job with something so oscillatory as these initial conditions. Did you have a question?
What is the physics of these oscillations? Why did they have
So
different scales, what size of scales and so on?
yeah, so it's just strong coupling early on between dark matter to undergo acoustic oscillations together with baryons. So it's kind of like coupling dark matter to photons indirectly. Okay, so it's the same physics as baryonic acoustic oscillations.
Just like a back reaction
Yes. But like, if you, yeah, only if you couple strongly enough. Even in my n=0 model, you could see that little bump past the cutoff, which I totally ignored because it's very small, but they always happen. It's just that they're very strong in models where you where the decoupling is very abrupt, and you can couple very, very strongly at early times, given the current balance. Yes.
So here the dark matter is only interacting with the protons, but not between themselves.
Sorry, but not,
There is no self-interaction between the dark matter.
there's no self-interaction. Yeah, correct. Not in these models. Again, maybe not too realistic when you dig into, some UV completions for where these operators could come from. But a first step in understanding what this physics actually does to structure formation.
So why not any of the other elementary particles, like protons?
Protons are the most abundant, and the easiest, yeah, okay, so I'll step away from like detailed, trying to build a detailed physical intuition, but you can couple to anything you want. You can decide to couple to just neutrals. Like that's fair, but there are models you can write down that'll couple to charged particles with the protons. They are, again, that's where the effect is the most intense.
It could couple with the electrons too, right? Because that's
It could
something-
couple with electrons too. Electrons are smaller, have a smaller contribution to the energy density, so you get a subdominant effect if you do that. But we have definitely done analysis with just purely, leptophilic dark matter that just couples selections.
Maybe dumb question, but
When you as well.
when you compare different ends,
But sorry, with
when you compare different values of
Yeah.
n, what do you do with the units? So the
Okay.
velocity is normalized with the
C.
so you fix sigma 0,
Yes.
and then you compare different ends, okay?
Mhm.
And then
And the way to think about it, why the numbers for sigma 0 come out different, I'm anticipating that maybe what you're saying. I'm gonna show my derivation here, I just wanted you to look over there. Is because the quantity that you're actually kind of more directly probing is that. It depends how that goes into, how momentum transfer cross section goes into your interaction rate, which is kind of a more direct observable, and how much is suppressed by the powers of velocity. Yes.
well, if you normalize with C, I would expect higher n to be to lead to weaker interactions.
Yes.
While it's not really, there's no clear hierarchy in this plot.
There's no, that's because I chose the cross sections to demonstrate a different point here. So I can move,
Also, these are different sigma zeros.
yes,
I see.
Yes.
Okay, now it makes sense. Okay.
yeah. Absolutely. Okay, so which brings me to the point of why did I choose to put these spaghetti right around here? I did this because we're trying to be clever. Before we actually had simulations of structure formation in cosmologies that look like that, we felt like there has to be a bound on these models that comes from the fact that we have any substructure in the Milky Way. In fact, if you just look at the CMB bound on these models, right, and you figure out what the momentum transfer should be given those bounds, you shouldn't even form a Milky Way. Right? That's how weak the CMB bounds compared to what we should be able to get from small scales really is. And so, but again, we didn't have forward models for these cosmologies. So what we did instead is we said, okay, here is a bound on warm dark matter, which is very nice, clean cutoff that we know of from SDSS, PanSTARRS, and DES. So that's where the cutoff is. And I know the cutoff isn't to the left of it because I would lose, that's my daughter's. I would have lost some of the substructure that I know exists in the Milky Way, right? So forbidden to move it to the left, I can move it to the right and not be hurt by it because I can hide this cutoff. I can lose structure on scales that I cannot see. So then what we said is, okay, so we don't know, I can't tell you what the subhalo mass function or luminosity function of satellites should look like in these cosmologies, but I can tell you that it will be suppressed more than this warm dark matter model, so long as I pack those initial conditions to be much more suppressed than the bounding case there, okay? So while I can't tell you how much you could move, for example, this curve, look at that lack of power and a broad range of scales there. How much I can move it to the right, in other words, how much I can decrease that interaction cross-section still, like, and be consistent with the data. I can definitely tell you that this guy is going to produce a lack of satellites beyond the 95% confidence limit that I get from warm dark analysis. So,
Vera,
yes.
is there sort of, I don't know, like particle physics justification for this power loaded? Sigma n, it can n, for example, be negative.
The n can be negative. That's not effective theory because these are the cases where your mediator is heavy compared to momentum transfer. Okay, you get positive powers velocity dependence. You get negative ones if you have a light mediator. So that's beyond the realm of effective theory of dark matter proton scattering, which, by the way, was developed for direct detection. So we just borrowed that language. But those models are really interesting because, for example, millicharged dark matter couples with V2 minus 4. Okay. And I'm not discussing it here for particular settings, so we can chat about that. All right, so imposing that, like, okay, if I have an initial condition that is much more suppressed than the bound on how much I can suppress via warm dark matter, those are going to be inconsistent with the data. Okay, so it turns out, and it's beautiful work that was led by an undergrad at the time, Karima Mari, over at UC. So here are the bounds from C and D, Lyman-alpha 4. So this is linear cosmology beauty, right? That we, spectral distortions even. But when you do this trick on each one of the models, so this is velocity independent and then higher powers of velocity dependence, you gain 3 to 5 orders of magnitude into the parameter space. Okay. Of course, this method is not going to give you detection. Right? I'm only declaring what's absolutely disallowed, but I'm not providing a way to actually go ahead and look for these kinds of features due to this interaction physics. Okay, so I'll come back to that one.
Why do the constraints behave this way as you increase the value of n?
Why did they? So I can explain this one for these ones. I don't have off the top of my head intuition. So the knee here appears at around the scale of the target particle. So that's a proton. Okay, so GeV. And then to the left is the scaling of the momentum transfer rate as a function of dark matter mass in the limit where dark matter is much lighter than a GeV. And on the right is the scaling that you get when it's much heavier than a GeV, and it like beautifully follows the shape of that curve. And something similar is true for the other two models, but it's not always as clean because our chi is not, the momentum transfer rate is not exactly directly an observer, but that's kind of the intuition. Okay. All right, now I have to make a decision of how much I need to skip because let me skip to my example number 3. So I'm going to skip off mixed dark matter. Ask me more about that if you're interested. Mixed dark matter is this beautiful model that beautiful to me because it messes with a really broad range of scales. And that's not something I can constrain in the same way with this like being clever theorist, putting everything under the cutoff and hiding that way. That's not something I can do that way, but I can use linear cosmology, which is what we did using the EFTO large scale structure. Ask Matthias more about it if he hasn't yet, given you a lot of details and you don't know it by heart. Nick is here as well. So we did that. We recruited Misha Ivanov, who's one of the members here, one of the experts on EFT. And we asked him, pretty please, can you help us modify our class code so we can do this higher order perturbation theory and fold in galaxy clustering data and do an analysis of something like mixed dark matter, and it worked beautifully. So that's what I'm not going to tell you about. But I do want to tell you about self-interacting neutrinos. So skipping over to neutrino physics, why did I get interested in neutrinos other than, well, they're probable by cosmology, is because they are arguably a mysterious portion of the standard model. They have a mass, they shouldn't, because they're all left-handed and you shouldn't be able to write a mass term within the standard model of particles that we know right now. And yet they do have a mass, they mix, they're really exciting, and you can make dark matter out of them. Okay? So why not, take a look at what high energy physicists have been thinking about in context of the neutrino sector of the Standard Model and see whether we can prove any of that physics using cosmology. So self-interacting neutrinos is this paradigm where you, beyond the weak interactions, you add a four fermion interaction, kind of like billiard ball scattering between neutrinos, but that would occur through a new mediator particle, through a new force if you want. And the reason you would do that is because that's what you need to do if you want to give neutrinos mass in some of the leading models for mass production, okay? Not a high energy physicist, so not the great person to give you details on this, but again, this idea of neutrino self-coupling to another mediator that we haven't observed yet precedes anything cosmological analysis related. This is the effective Lagrangian, and the key parameter of interest here is this G effective Fermi-like coupling constant. So that's a 3-parameter. Okay, so this particular model garnered a lot of interest in the cosmology community. Maybe I want to say 10 years ago, something like that. I want to say a few years ago, but it's really in my time frame, so probably 10 years ago. When people realized, and there's been a bunch of papers on this, many of which were led out of Princeton, so I highly encourage you to talk to folks there as well. And the reason people paid attention to this model is because it looked like a solution to the Hubble tension. Yes, you must have heard of that. Self-interacting neutrinos solve the Hubble tension, okay? Spoiler alert, they don't, you know now. But I want to show you how we've proved them in recent years in new ways, and why we may want to still be thinking about this model more broadly. Okay, so here is an illustration of the mass profile as function of cubic radius. This is going to show you a few wavefronts in different fluids. So different colors correspond to different fluids. Neutrinos free streaming are red, and purple, this peak that kind of lags behind the red, are self-coupled neutrinos. So these are neutrinos before they're allowed to free stream, and they're disallowed from free streaming because of this new interaction. So these are sticky neutrinos, if you want. Okay, so what happens, and I'll just play this one more time, just for intuition, is free streaming neutrinos kind of disperse very quickly. And their wavefront kind of leads ahead of where the baryons are. And so one of the cosmological effects is that they tug on the sound horizon scale, make it a little bit bigger. And that's where the solution for the Hubble tension idea comes from. Okay, the self-interacting, not the free streaming, the self-interacting neutrinos make the horizon a little smaller, and that's the solution for the Hubble tension, whereas the free streaming do not do that. Okay. So let me show you the matter power spectrum, which is of high interest to me. So here's again my transfer function, the ratio of the power spectrum in self-interacting neutrino cosmologies versus the scale. And the difference between dashed and solid is just in adding the neutrino mass, the sum of neutrino masses. So you suppress small scales when you add the mass. So you really should be looking at the dashed curves there as the more realistic representation of this cosmology. The two colors represent two strengths of the interaction. And so the weaker interaction pushes this excess power bump towards smaller scales, whereas if you have a stronger interaction, the bump is at larger scales. As you might imagine, the location in K space of this excess power is the size of the sound horizon when neutrinos begin to free stream. So you can move this around by adjusting this free parameter, the strength of the coupling. And so where the field was, I want to say 6 years ago, pretty sure this, 2019, was this. So Kreisch and company here at Princeton did an analysis of Planck 2015 data. They found this posterior probability distribution for G effective. And so what I want you to notice is this giant peak at non-vanishing G effective. So there's a preference for some amount of neutrino self-scattering. New Planck data came out, and this bump went down quite a bit.
What is dash and solid here?
what is dashed? I think they're separating the weakly interacting and strong, I didn't call it like that, strong mode and a weak mode. And the reason they separated is really interesting. So I was postdoc there at the time, is that this is a nightmare to sample this posterior because it's multimodal. Right, so they were, I think, being clever with how they were doing the sampling there. So it came from separate analysis. Okay, so I want to take a step back and just introduce really quickly to the scene a new observable, which we started playing with a couple of years ago. This observable is not new to the cosmology community, but what I want to stress in the next couple of slides is how much it's evolved in the recent just couple of years. Okay. This is the Lyman-alpha forest, and of course the idea is you look at the bright quasar, you take the spectrum, and in that spectrum you see a forest of lines, a thick forest of lines that correspond to Lyman-alpha transition at different redshifts. And the reason these are absorption lines is because as you ray trace through large scale structure, your photons are going to be absorbed by structures along the way, by neutral hydrogen in structures along the way. Your flux is proportional to the minus tau, where tau is the optical depth. And the optical depth knows about, so this is just an approximation, but it knows about the density, the baryon density in the medium. So here is your probe of the baryon density fluctuations along the line of sight. Okay. Now,
beta is
beta is somehow
depends on what?
it depends on a couple of things. It depends primarily on, and most interestingly, maybe on the relationship between the temperature and the density field in IgM. Okay, which you have to either calculate using the fluctuating Peterson approximation, or you have to simulate it, you have to model it in some way. And maybe anchor some observations. All right, so what I want you to note though, this particular probe is not telling you where galaxies are along the line of sight. What it's telling you is where uncollapsed clouds of IgM, Jeans scale clouds, so pressure supported structures, where they are at redshifts between, let's say, 2 and 5. Okay, so when we probe the forest, the saturation here corresponds to overdensities that are on the order of a few, delta of like 2. Okay, so we're not probing galaxies, we're not probing things that are going to become galaxies, we're probing a really mildly nonlinear regime at these high redshifts. Okay, so of course, you know, over the last couple of decades, people realize this is really interesting cosmological probe, and you can invert what we measure to put some data points on this matter power spectrum, just like we do from other observables. And coming back to my plot, the reason I like that probe is because it really covers the regime of scales. So this is in moving units, right? So you have to account for different redshift coverage and things like that. But it probes the scales that no other probe really reaches the same way. Okay? This is not exciting if all you're looking for is just a cutoff in the power spectrum and putting bound on that, because you always will win by looking at the smallest scales you can reasonably reconstruct or constrain. But it is really exciting if what you're looking for are features that can hide in the forest at those scales. Okay. All right, so let me see what I want to tell you. Okay, I'll tell you about this. All right, here's a twist in the story. Up until just a couple of years ago, we've been kind of relying as a community on, and we still rely on data from EBOS for the Lyman-alpha forest for cosmological purposes. This is some of the best data sets that we have. There are other surveys with high resolution spectroscopy from various telescopes around the world. But EBOS data was turned by Chambarier and company into this reduced likelihood So ignore this for a moment and please don't get too disturbed by this separation just yet. You can get disturbed later. But here is the linear power spectrum. So this delta here is the amplitude of the power. So it's a proxy for the amplitude at the right redshift, the right scales, k of about 1. And the N effective is not the radiation, radiation in the early universe. It's actually just the tilt of the power spectrum at the particular scale that the forest probes. Okay, so you have the tilt versus the amplitude. So this is what we've been using for cosmology until recently. Here's where Planck lives in that space. Here's what the Lyman-alpha forest from Charbonnier et al. EBOS likelihood lives. So this is horrible, right? This is a tension if I've ever seen one. But that's where we were. This was the best data that we had until recently. This likelihood was built on the simulations, calibrated on the simulations of the forests that were available at the time. Okay, so some of the things that this discrepancy led to was, for example, if you analyzed these two data sets, the forest plus the Planck, for self-interacting neutrinos, which we did because we just wanted to see what happens. This is the situation that we got. So here's your G effective. I don't know why this should not be the vertical axis. I'm sorry, I don't know what I did here. So here's your G effective. This is the posterior probability distribution, so no units here. Here's Planck, a little blip left over, but not much there. And then you combine with Lyman-alpha forest with Charbonnier likelihood, and you get a 5 sigma detection of this neutrino self-interaction. Okay, so neutrino free streaming, this plot screams, is delayed until redshift of about 8,000 or so. There's some new interaction in the neutrino side. And the reason that that model is so preferred over lambda CDM, over G effective of 0, is because it can reconcile this tension. Okay, so this preference is heavily driven by the Lyman-alpha likelihood, but it didn't ruin the fit for lambda CDM. Interestingly, the fit for lambda, sorry, for CMB data, the fit for CMB data stayed as good as it did with lambda CDM. Okay, so we put this out full well knowing that this is going to raise eyebrows, but this is taking the data at face value. Okay, fresh look at Lyman-alpha forest. This is what we get. So in the meantime, 2 groups, one led by Misha Ivanov over at MIT using EFT modeling of the Lyman-alpha forest, same data, but using a different, higher resolution, bigger simulation, Sherwood simulation, hydrodynamical simulation of the forest, to condition the bias parameters in the EFT approach. Here we derived the likelihood that lives now here, again, still not fully consistent with Planck under lambda CDF. And then another compressed likelihood came out of the PRIA simulation, which is one of the largest currently available highest resolution Lyman-alpha simulations out there. That includes all sorts of new physics that we now understand to be important for this modeling, like the patch ionization, helium ionization, and so forth. And there is good and bad news, right? So these curves here are under lambda CDM. So they don't agree with the original Charbonnier likelihood, okay? That's okay, we can live with that, better simulations. They agree with each other reasonably well, but they still disagree with Planck. Okay? Maybe less egregiously so, but they still disagree with Planck. Okay, so what we did then is we partnered both with Simeon, who's also, all paths lead back to IAS. He was also a member here, same time I was, and then Misha, Ivanov as well. And we analyzed the self-interacting neutrino model, and this is the posterior that you get for Planck for self-interactions. So there's marginal agreement with the EFT likelihood in that case. So we proceeded to compute the upper bounds from combined analysis of Lyman-alpha under both models separately, and using the ZBAO, which changes nothing about our inference with Planck. So I would argue that this EFT likelihood we have here does not allow any strong interactions in self-interactions in the neutrino sector, and it presents the best bound that we know of on this specific physics for cosmological observations. Okay, so at 9 more minutes, what are you gonna give me?
See 5
5.
questions.
Okay, so I'm gonna set you up maybe for asking me some questions. Let me see. I'll just show you this and I'll say Priyank, who's a postdoc in my group now, has combined the two, the paradigm of sterile neutrino dark matter. So non-thermal relic that looks kind of like warm dark matter, but not really. And use this approach of adding self-interactions to the neutrino sector to enable the production of sterile neutrino dark matter. And if you have a model like that, you're touching on a few points in cosmic history. So you're changing the neutrino sector and changing the free streaming of neutrinos, but you're also producing all of dark matter using this specific channel. So you can use cosmological probes to put bounds of this on models like that. So here is the mass of sterile neutrino dark matter produced in this way versus its mixing angle with active neutrinos. There are previous bounds from X-ray observations of galaxies. Ask me about that if you're interested. And there are bounds that come, this dashed horizontal line here comes from invisible Z with, okay, so the decay of the Z boson measurements in collider experiments. And where the Lyman-alpha forest seems to be able to go is beyond the bounds that we can get from lab experiments. So I find this fascinating. And I find it very worthwhile to think about the synergies between what we're learning about fundamental physics in lab and what we're learning from the sky. And just as an aside, there's a lot of billions of dollars and euros invested in neutrino experiments. Who recognizes these pictures, by the way? Do you guys? Does it ring a bell? Yeah, that's good. But do you recognize the right hand? So does anybody know what the right hand side is? I have seen it.
The code.
Yeah. What's that?
It's an abandoned line.
It's abandoned. It's not abandoned. There's so much activity in it. So I was there just a couple of months ago. This is a mile underground in South Dakota in Sanford lab. I think it's a $5 billion experiment. And I'm showing this. This looks just like a cat. Like, what is this? Why is this even interesting? Okay, this little toy crane. This little toy crane is maybe like a 6 or 7 story building high. And the little dots over there are people that are, I don't know, a mile away from you there. It's an enormous effort, is my point. It's just daunting how much money and effort is going into these kinds of experiments to do very similar things to what we're doing in cosmology. Not the same, definitely complementary information, but a lot of it is going to be echoing the things that we hope to find in cosmological observations in the next few years. So this effort really is worth thinking about in greater context and connecting to experiments like this. Okay, and I knew I prepared like 3 times as much material than what I can get to. So I'm just gonna go to my concluding slides. I told you about 2 models out of 4 that I was hoping to tell you about. There's a lot of effort in the community, especially in the dark matter community, to push towards modeling of those small scales, because we understand that the methods that we've applied so far are really good at putting bounds, but again, not as good, not enough to actually look for signals in the new data, like the things that we'll learn from LSSD and beyond. And so there's a lot of modeling efforts out there. But I also want to mention their observational efforts that our community is maybe not as familiar with. And so I want to give a shout out to one such thing that I got connected to very recently, and this is through our Templeton Foundation funded project. This is a large scale project that we're working on between several institutions in SoCal. But one of the inspirations for looking at the Lyman-alpha forest is an effort like this. So this, what you see here, is not a simulation. This is a 3-dimensional tomographic reconstruction of the forest itself, first of its kind, done by observers over at the Carnegie Observatories in Pasadena, California. The way that they've done it is they basically use galaxies, dense sightlines towards galaxies rather than quasars in order to reconstruct in 3 dimensions distribution of gas in the universe. Okay, and at those redshifts that we usually talk about, 3-ish or so. So to me, I'll get questions like, well, but how much resolution can you get doing something like very little, you guys, very little before you ask me that. But the thing is, this is the first effort of its kind, right? This is the first moment that we have these, across the line of sight correlations to calculate. And so the question to me is, what can we do as cosmologists with data sets like this? So we came together as LARC, which is Lyman-alpha Forest Collaboration that involves UC Carnegie and UC Riverside. And this is a truly interdisciplinary in astrophysics context, but even more broadly, you can ask me about that later, collaboration that brings in theorists like myself who think a lot about dark matter, simulators like Simeon Bird and company, observers from Carnegie, and a whole bunch of data scientists, statisticians, and machine learning engineers who are really into figuring out how to speed up simulations and body simulations using machine learning models and so forth. So what we want to do is we want to produce forest simulations in beyond CDM cosmologies to really understand structure of those scales in some of these really interesting models. We want to calibrate the astrophysics that we put into those simulations through state-of-the-art observations that these folks can access using the big telescopes. And we want to think about what can we do with tomography like this. Maybe not immediately right now, but maybe tomorrow in the next generation of these kinds of surveys. And then perform something like probabilistic analysis across scales. I'm really excited to see what comes out of this. Okay, I'll give up my summary, which is not summarizing, which is summarizing more than the points I was able to make, but thank you for your attention and for the questions. I'm happy to stop now.
So, Kevin?
In your constraint plot for the Lyman-alpha, I'm just curious if there's a notion of whether to listen for problems in the simulations.
Sorry, it's saying, is there
a notion of what are the most important knobs in the simulations that change your constraints around them?
in the sim? Oh, you mean like the astrophysics knobs? Yeah, so if you talk to Simeon, I think one of his arguments is that one of the important things that we didn't realize before to include is this patchy reionization effect. So this is something that we think contributes, besides from other things, contributes to the difference between EFD likelihood that was calibrated in simulations that don't have that physics and the likelihood for PRIA. So for example, that's one of the things. The other thing that is critically important is this relationship between temperature and density, which is, calibrated somewhat, but actually can be done a lot better by direct measurements of temperature in the CGM gas, which is something that Gwen Rudy over at Observatories is doing. So this is one of the relationships that this whole inference relies on. Great. Yes.
I have 2 questions. Do people now understand what's wrong with the Chauvet likelihood, like this EBOS likelihood, for it to be so far away from everything else in space? Is it something about the model? And if it's being recorded, you can just say offline.
I mean, again, we can discuss offline, but I think there's several things going to it. One of the things I've heard of is I have never gotten a very satisfying answer. I've never seen a paper written going like this. Things what's totally wrong, but there are things that have emerged. One of the things is just larger simulation with higher resolution. That's the argument. That's like an argument. I feel like sure, plausible. The other thing that I've heard is this along the lines of like the physics was not enough that was included in the previous simulations. We now understand the IGM a lot better than we did 10 years ago. And then in addition to that, low ret. So when Simeon and Misha unpacked this reduced likelihood. By the way, it's a reduced likelihood because you pack all the information from the forest into two numbers, the tilt and the amplitude, right? Like this ellipse, right? So that doesn't tell you a whole lot, but that comes from a whole range of redshifts. So what they did is when they unpacked it and tried to model redshift by redshift, they saw that low redshifts are disagreeing with some of the high redshift bits. So they rejected them in their reanalysis. And the vague intuition, I think, has to do with some metal lines, I want to say, but like this, don't hold me to this is a little stretching she seems to agree, so.
No, I actually, this was my question, whether you have to worry about the contamination, not just from the metal lines, but Lyman-Werner absorption from molecular hydrogen too is in the UV as well, so. I don't know what they do observationally. Do they just assume that everything comes from Lyman-alpha? Is that the idea?
No,
or
I think
is
that
there
there are
space to?
DLAs and Lyman limit systems are masked out, so you do deal with those. You model them, you forward model them and you deal with them. You don't just blanket assume that everything's coming from Lyman-alpha. You don't know how much metal lines are modeled. I'm gonna ask Simeon, I can tell you what he says, but I don't know. Yeah. But this kind of like jackknife tests are now possible and much more transparent to the community, I feel like, than they were before. So that's a big advantage, and I think the reason why people buy these and maybe were skeptical of what was happening with Lyman-alpha before. That's my sense, but not quote me.
Well, let's continue this conversation over lunch and thank you for your
And then put this up, because this is made for us by a professor at the Cinematic Arts at USC. I gave her some real, Feynman diagrams for dark matter interactions in one of our simulations. And these creative people, this is how you know you have artists. Anyway.